All right, can you all hear me?
Yeah.
All right. I need to open up one more file. All right, so I want to talk about our next lab, but before I get started, I am grading your labs, and I think the way I grade the labs, I've been grading them by sections, so just because of the way Canvas is set up. So your group, I have graded the DC circuit analysis lab and the scope lab. And I sent an email regarding the scope lab, and my concern was regarding the scope lab is a lot of people who did the scope lab just showed me that they knew how to get the signal in the scope, but the video you should also explain how you obtain the measurements, okay? Because it says in the lab, show me that you know how to use, show me in the video that you know how to use a scope. Part of that is showing someone how you get the information from the scope. It's not just about showing how you get the signal, but showing how you get the information from it, because otherwise, what's the purpose of it if you don't know how to get the data from it? And I was concerned because last semester everybody did it that way. Everybody showed in their video how they got their measurements. I will have comments regarding the DC circuit analysis lab. One of them that's a little bit troublesome is when I ask you whether or not two values agree, and a lot of you still focus on the percent error instead of looking at the overlap between two measured values. So let's say I have two measurements. And the question is, do these two values agree? And what you do is you look at whether these two ranges overlap. And I think a lot of people still don't understand that when you make a measurement, you don't measure one number, but you measure a range of value because you got to take into account your uncertainty. Okay? And so does this range, and this range overlap? If they do, then they agree. Not the uncertainties overlapping, but the range of values represented by your measurements. Do they overlap with each other? That's the question you have to answer. That is objective. Okay, as scientists, you want to be objective, or as objective as possible. You don't want to be subjective, right? This is not politics, all right? Or philosophy or whatever. We need to be objective, and especially nowadays with the way things are in the media, you want to be as objective as possible. Okay, so when you say my value is close, what does close mean? Define close. That's a subjective statement. Okay. So I asked this question over and over again, and I wanted you to be able to say that this range of values overlaps this range of values, if they agree. If they don't agree, then the ranges don't overlap, and there's probably some sort of systematic error there. Okay, so that was the big issue I noticed in the lab, other than missing units or sig figs. Okay, but anyway, what I'll do is once I've graded the other sections lab, I will send out a list of comments. Okay, so in the last two labs, we only have two labs left. That's it. In the last two labs that are left, hopefully you will correct these mistakes. And when you take 215, you're going to be asked the same questions over and over again. And we keep asking the same questions regarding whether two values agrees, because you need to understand that you have to be objective in that assessment, not subjective. Okay. We don't want to be like the way the media is nowadays. Okay? All right. So our second to last lab is the Transient Lab. I'm going to talk about the first two parts of the lab today. And the third part I will discuss next week. Okay? This is not a long lab. I know it has 3 parts, but I tried to make it so it's not very long. And I hope it's not very long for you. It's the measurements are, I think, fairly straightforward. There are issues you have to deal with because of our signal generator, but it shouldn't be too bad. Okay, and I try to structure it so it's not a very long lab report. However, the last lab you do this semester, which I will talk about next week. So next week I want to talk about the third part of this lab and this lab. This is an extremely long lab. If you wait till the last minute to do this lab, you'll never get it done. Okay? It is extremely long. It'll probably be the long, unless you took 215 and you did the driven damped harmonic oscillator lab in 215, this will be the longest lab you've ever done at Sierra College, at least in physics. Okay? So just be aware. All right. So let's talk about the transient lab. And what do I mean by transient? Basically, we're looking at how a circuit responds to some input signal. So one of the things you have to do is review the RC circuit. So in this lab, one of the things we're going to do is to learn, basically to go over the RC circuit and verify the equations for the RC circuit, but also gets you to become more comfortable using the scope. So the circuit we're going to look at looks like this. We're going to have a power supply. And we're not going to use a DC power source because once you charge a capacitor with a DC power source, after a little while, the capacitor is fully charged. And if you observe the scope, you're just going to get a horizontal line for the voltage, okay, after you wait a long time. That's boring. So actually what we're going to do is put in a square pulse. Mm-hmm. So you're constantly charging and discharging the capacitor. Okay? So you're going to be constantly charging and discharging capacitor. So here's your circuit. It's basically your signal generator, your resistor, and then your capacitor. And you can do that all on the proto board, right? Except for this. Obviously, you can't put the signal generator in a proto board, but you can put these components on the proto board. This is going to be 100 ohms. And this is going to be 4.7 microfarads. And we're going to look at the voltage across the capacitor. And if you remember, the voltage across the capacitor is given by this equation. I hope you remember this equation. Okay, I'm not going to have you derive that equation. Hold on a second. Let me fix something here so you can see better. Okay. Everybody can see that okay?
Yeah, yeah.
Okay, all right, good. So this is the working equation here. And for the lab, the theory section, I'm not going to have you derive this equation. Okay, but you do have to understand how the RC circuit works. So what we're going to do to verify this equation, where does it come from? I apply Kirchhoff's laws to this circuit. Right, I solve a differential equation and I solve for Q. Q divided by the capacitance gives me this voltage. So you're going to put in a signal that looks like this, and the capacitor is going to charge and discharge. So it'll do something like this. Okay, so you're going to be able to observe the capacitor signal on the scope. Now, unfortunately, our scope only has one channel. Ideally, you really should have a two-channel scope. One, so you can see the power supply voltage, and two, so that you can see the capacitor voltage. And I'm going to demonstrate that circuit to you this morning, but I'm going to use a scope that has both channels, so you can compare them, at least in the video. Okay? What you're going to do is obtain the value of C from some of these, from a measurement. We're going to get this value of C. So the question is, how are we going to do that? And there's multiple ways we can do it with an oscilloscope. One of the ways we normally do it when we're on campus, I can't do it with the scope. Okay? Just because it doesn't have that feature. But there's another way we can do it, and that's what we'll look at. We're going to measure the voltage across the capacitor with a scope. Whoops. And you'll observe this signal. To do this, you're going to actually look at the voltage across the signal generator, make sure that this amplitude is 1 volt, then remove it from the signal generator, and then put it across the capacitor. Make sure that one end of your capacitor is tied to the ground. In other words, you want the capacitor to be second in your circuit. Not the first one, but the second one. And the reason why is because the scope, one of the inputs on the scope is grounded. And in reality, it's not earth ground in our scope, but it's what we would call a common ground. If you put the scope here, you'll bypass the capacitor. And for people who work, for example, with transformers, they get shocked from it. It's dangerous. Okay? So you need to have the capacitor here second in your circuit. One end of the capacitor has to go to the power supply negative. The black wire. Is that clear?
Yes.
The video, there's a video for this lab that Tyler created. I sent you the link last night. He spends a lot of time talking about that because that's a common issue students have. Okay, and this is something where this is one of the things you're learning as you're doing these labs, is learning that, you know, a scope has a ground. Not all scopes are like that. Most scopes are grounded. And like I said, the ground on this scope is not like a earth ground. It's a different kind. It's a common. Okay. There are some scopes that have what's called a differential input, so you don't have to worry about the ground. But we don't have one like that. Okay. So what are we going to do in this lab to verify this expression? What you're going to do is the following. Here is the signal for the capacitor. Okay? What you're going to do is you're going to measure how much time it takes for the capacitor to charge to its maximum voltage. Okay, you're going to find the amount of time it takes for the capacitor to charge its half its maximum voltage. So if the maximum voltage you set is 1, you want to find out how much time it takes for the capacitor to charge to half its maximum value, which is a half a volt. You're going to measure this time. From that knowledge, we'll be able to calculate C. Is everyone clear on that?
Mm-hmm.
So, if you want to get accurate values of this one and this one, what do? On the scope, you want to make this trace. This is called a trace. I know some people call it a graph in the scope lab, but this is a trace. If you want to make good measurement, you want to make this piece as big as possible on your screen. You want this to be as many divisions as possible, and you want this to be as many divisions as possible. Okay? So Chase, why is it half? That's just a convention we choose usually. Because how do you measure? I mean, you can't do the full, you can't do, you can't make these two equal to each other because t would be infinity, right? But we normally choose half. Half is common, especially, it is a nice number, okay? We're going to see the natural log of 2 come in this problem. So that's a common thing. But if you've ever studied radioactive decay in chemistry, you talk about the half-life. It's common to talk about when something gets charged or something gets to half its maximum value. That's why we're choosing half. It doesn't have to be half, it could be a third. But that 1/2 is common. So what you're going to do is measure this time. Okay? And so the question is, how are we going to obtain C from this? So let's do some math. And I guess
Professor?
Yeah.
On that circuit with the signal generator, why did we set the voltage to 1 volts?
It's just arbitrary. You can choose 2 if you want.
Okay, like is there a specific reason for why we do that?
To choose 1 volt, it was just arbitrary. There's no specific reason. Well, okay, I got to be maybe a little bit more clear. So you're saying 1 volt as opposed to 2 volts?
Yeah, like why 1 volt only?
It's a nice number.
It is. Okay.
No, but there is another limitation. These signal generators are limited. The output current is limited.
Yeah.
And when I played around with it, the 1 volt worked best.
Okay.
But in reality, I mean, if you have a good signal generator, it doesn't matter.
Oh.
Okay, I just chose, I mean, really this is supposed to be an arbitrary, it could be any value. Okay? Because let's take a look at this equation. Let's divide both sides by delta V, the power supply voltage. And we want this to be 1/2. Doesn't matter what this is, right? As long as this ratio is 1/2. That makes sense? I mean, really, the only reason why I chose the 1 in this particular case is because of the current limitations of our signal generator. But otherwise, it's arbitrary. You can make this 4 and this 2. Still going to work, right? So I divided both sides by the power supply voltage and set it equal to 1/2 because we're trying to find this time in which this occurs. Okay, I'm going to do 2 steps at once, if you don't mind. And I'm going to get the following. Are we okay with that? Okay, so guess what I'm going to do next? I'm going to take the natural log of both sides. Okay, then we solve for C. Oh wait, what do I have to do now? There's a negative sign here. What else can I do? Let's flip this over. That gets rid of the negative sign here. If you don't remember that, you got to review your logs. Okay? So you're going to measure T1 half, you're going to measure R, and you're going to measure this. This is a measured number. Why is it a measured number? Why am I saying it's a measured number?
Because you're measuring the half.
Yeah, you're measuring this ratio, right? Actually, no, it's 2. This is flipped over, right? So we're measuring that. So we have to figure out the uncertainty in this thing. Okay. All right, so you're going to do this for 3 different frequencies. And you might notice an effect as you raise the frequency. You're going to do it at, let me double check, 50 hertz, 100 hertz, and 250 hertz. Okay? This is the only one where you're going to do 3 measurements. The next part, you're only going to do 1 measurement. So you're going to do 3 at 3 frequencies, and you should get the same value of C. Now, question is, what is R? What is R going to be? Anybody want to guess what R is?
Is it the resistor we have plus the resistance of the frequency generator?
Yes. This R is your total resistance of the circuit. If you do not account for this resistance, you're going to be way off. So last semester when I did this lab, we did not account for this and the results were not good. Okay? So and so we need to account for that. This is why you did the second part of this, the lab in the scope lab. So you're going to have to actually copy and paste that table from the scope lab into the appendix. You'll see it'll say the instructions into the appendix of this lab. And then you're going to use your measured resistance to calculate the total resistance of the circuit. So this is not just this value, but it's this value plus the resistance of the signal generator. Okay? This is our total. Where R sub S is the signal generator. Everybody clear on that?
Should that 100 ohms be the one that we measure actually?
You're going to measure that. It's not going to be exactly 100 ohms, right? It's going to be,
Yeah. Mm-hmm.
you know, whatever the meter gives you. Why is it so? You mean the signal generator, Chase? It's 50 ohms. It's around, well, it varies, right? You guys measured it, right? You guys measured it to vary from, I mean, when I did it at at 10 hertz, I had like 80 ohms. That's why for some of you, I was concerned that that number's low, but then I realized that there's actually different versions of that signal generator. When you turn it on, it says a name on it, and I've seen different names on the signal generator when you turn it on. Because I've had 2 versions of the signal generator, and the times I turn it on, it's a different name. When I turn mine on, there's a word that starts with the letter X that comes out. And I don't know what yours looks like. So it might depend on the manufacturer. There is generally, on these kind of things, there is a capacitor just before the output of this thing, which is used to get rid of DC voltages. And if they vary that capacitor, that's going to vary the resistance of really the right term is not resistance. It's impedance. It'll change the impedance of your power supply, especially at lower frequencies. So I just said in the scope lab, oh, this might be a little low. But we'll see the effect in this lab. So you'll see the effect. So if your value for this is low, we'll see the effect of it. Okay? And you might need to remeasure it. Because mine was 80 ohms at around 10 hertz. I forget what it was at 50 hertz. I forget. But as the frequency goes higher, it approaches, asymptotically approaches 50 ohms. Is that okay? So all you got to do is set the circuit up and measure this time and then swap out capacitor, repeat. Now, I'm saying not swap out capacitor, change the frequency and repeat. This signal, because of that capacitor, when you change the frequency of the signal, this will change too. Don't trust that it's going to stay the same. So when you change the frequency, you have to go back and make sure that your signal is 1 volt. You got to make sure this doesn't change. So for each frequency, you got to make 2 scope measurements. 1, you got to look at the signal across the generator, and 2, you got to measure the signal across the capacitor. Okay. Any questions?
That square signal is not totally above the zero line, right?
I'm sorry?
The square signal that we have, that is not totally above the zero line, right?
What do you
There
mean?
would be some like in the negative region as well, I guess.
Yeah. I mean, if
Okay.
you can do this, right? It goes the same amount above as it does below.
Yeah, it somehow looked in that like it was only above the line.
Yeah,
But yeah.
this one's above and below. If you ground your input, if you ground the scope and put the horizontal line right at the along the axis, and then you look at the voltage across the from the scope, you'll notice it. It'll be symmetric above and below.
Yeah. Mm-hmm.
Okay. Okay, so before I go on to the next part, we got to talk about one more thing. How do we calculate the uncertainty in the measured value? I'll get back to the other part. Let's talk about the uncertainty in the measured value. Sorry, I was getting ahead of myself. I want to get delta C. There's 4 measured quantities here. What are they? What are the 4 measured quantities?
There is T half, there is R, there is delta V sub C.
It's this, right?
Mm-hmm.
So there's 4 measured quantities there. We're assuming this. We want to set this to 2, but there's an uncertainty into that. And so we want to calculate let's do this first of all. Before I do the calculation, I want to look at this ratio. Let me write it here. Let A equals delta V over delta V sub C. Okay? So let's let A equals delta V over delta V sub C. And let's say I want to find delta A. Okay, I want to find delta A. What is that going to be? I got to take the derivative let's see. These are weird symbols. I was too lazy, I didn't put the extra delta symbol. Right, isn't that the case? And if you do it correctly, you'll get the following. I factored this term out. Okay? So that's delta A. So we know what delta A is, right? It's given by this expression. And this ratio is 2, right? I don't have enough space. Never mind. Let me, I want to copy this here. You can verify this after class. Okay, so now I want to calculate the uncertainty in C. Now that I know what delta A is. And I'm going to write this in the following way. First of all, I'm going to do this. And the reason why I'm doing this, because when I start taking partial derivatives with this log function, have fun. If I leave it like this, to me it's going to be a pain to calculate this log function. But if you want to do it, go for it, you know. So delta C is going to be what? It's going to be the partial of C with respect to T1/2 plus the partial of C with respect to R. That one's easy. Plus the partial of C with respect to A, which you calculated over there, okay? So what does this turn out to be? And by the way, for the inductor, you're going to do something similar, okay? What is the partial of C with respect to T1/2? What is this one? Follow my math. Okay, this is the fun one, okay? That's delta C. Any questions?
Although it does not matter, but we can put an extra negative sign for the R square.
You want to put that in here?
No, on the second one.
Oh, on this one? Yeah, you can, but it's, yeah, I didn't put it in because it doesn't matter.
Yeah.
If this was calculus, if it was a math class, it would matter. Yeah, because I square it, I ignore it. Right, both of these have that negative sign that I ignored.
Yeah.
You're going to do the same thing for the second part too. Okay, are we okay so far? Now the other thing too is we're going to calculate this measured C. So you're going to get this. You're also going to calculate it, compare it to the capacitance value. You can actually measure the capacitance with the multimeter. Okay, so let me show you. Well, I'm going to switch cameras so we can show you. I'm going to show you the circuit. I'm going to show you how to measure the capacitance, etc. So let me switch cameras on you. So I'm going to disconnect my microphone. So the sound might be a little different. And okay. So I want to show you, first of all, your multimeter, the big one, comes in the box. There is a little plug. Did you guys notice this little plug with the multimeter?
Yeah, I thought it was extra.
Yeah. So you can put the capacitor. You notice how I put the capacitor in? And it's polarized. It's polarized. So if you look at it, it'll say one side's plus and one side minus. The capacitor we're using is polarized. Okay? So you got to put it in correctly. If you don't, the capacitor will pop. Okay, and so then all you're going to do then is put this thing, and you don't have to do it with this. You can just use the clips, okay? But you can just put it right here like so. And then you put this is a different capacitor, but this will give you the capacitance value. And then you can get the uncertainty from the manual. Okay? That's it. You don't even have to have these in there. Does that make sense?
Mm-hmm.
Okay. So you can use that little extra thing in there. Yeah, it looks like some extra piece that's in there. It's like, what's it for? You can characterize transistors, etc. with it. Okay, so let's take a look at the RC circuit. And I built my RC circuit. I gotta be careful. On the proto board, I used to mess that up. Okay, I gotta put it back together. Hold on a second. Oops, I put it backwards. As I get older, my eyes get worse, so it's hard to see. All right, so hopefully it will work. I also want to do one thing. I want to show you the quality. I want to compare the quality of our signal generator to a fancier one. And I'm not sure why something's not working here. Give me 1 second. weird if things always go bad when you should do it in class. My concern is I don't have anything on my display.
Your generator is not on, I think.
I'm not using this one. I'm using a different one
Oh, okay.
because the signal is clean. Oh, there it is. It wasn't. Sorry about that. Can you see the signal on the scope?
Yeah.
The white is the, not the white, the yellow is the signal generator. I'll spread it out because that's really what you want to do. The yellow is the signal generator. The orange is the voltage across capacitor. Okay? And so in your case, you're going to have to do the two measurements separately because this particular one, I can show you both inputs. Take a look at the yellow signal. This is the signal coming from a good signal generator. Look at how it's nice and square, right?
Mm-hmm.
Very nice and square, right? Okay, so I'm going to switch power supplies now and show you what this guy does. This is the cheap $20, $30 one. The other one's back here. I don't know if you can see the blue screen it's on. Hold on, I have too much stuff on it. But I have a signal generator back here behind this rod stand. And it's a $500 signal generator. Gives you a nice, clean, square pulse. So let me turn the voltage down. And then what I'm going to do is disconnect the power from it. And then use our signal generator. Just so you get a comparison. Just to the quality of things. Okay, can you see the signal from the signal generator?
Yeah.
Is it square anymore?
No.
No, it's not that good. Okay, so that one of the issues is we're going to be dealing with in the next two labs is the quality of the signal generator. Its input is limited, its output is limited, the current is limited, and you're going to see the effect when we do the last lab. We're going to have to use very low voltages. So the signal generator I have in the back, you can barely see it. It's blue face with a blue background. That one gives you a much nicer, much cleaner signal. Okay, so that's one of the issues we're dealing with these labs because we're doing them on campus. We're doing them online. Okay, you're stuck with a cheapy power supply, but it'll work. It'll kind of do the job. All right. Okay, so I'm not going to demonstrate the other circuit, but I actually have the RL circuit on here too. And I want to show you for part 2, you're going to use a resistor and you're going to use this thing. This is called the inductor. This is the inductor we'll use. You should have 2 inductors in your kit. They're 2 different sizes. You see them? You want the small one.
Mm-hmm.
For some reason, the small one has a higher inductance. Okay? So let's talk about the second part of the lab. Let me switch. let me go ahead and connect my microphone. I know we haven't discussed inductors, but the second lab, or the second part of the lab, your circuit's going to look like this. And you're going to do these same uncertainty calculations in the second part of the lab. So your circuit will be this. You're going to have your signal generator. You're going to put a device called an inductor here. It's 10 millihenries. And we're going to talk about this in class today. And you're going to measure the voltage across the inductor, the resistor. And you might say, how come we're doing the resistor this time and not the inductor? And the reason why is because it's actually easier to observe the signal. I'm trying to make it easier for you guys. When you look at the inductor, it's very difficult to observe the signal. I mean, you can play around with it and you can switch them in your circuit to see the difference. Okay? But it's actually easier. And so this is one of the changes I made in the lab. So the new version has you measure the voltage across the resistor, not the inductor. I didn't make the change, but I forgot to put the change in the file that you had before yesterday. Okay, so you're measuring the voltage across the resistor. And you're going to do the same thing. Now, what's an inductor? Okay. An inductor is a device that opposes a change in current. The voltage across the inductor, the magnitude of the voltage across the inductor is L times di dt. If you apply Kirchhoff's laws, and you solve for the voltage across the inductor, you'll get the following. And the voltage across the resistor is this. Let me write it somewhere else. So you set this up using Kirchhoff's law, just like you would do for the capacitor, okay? And then you solve the differential equation, which is easy, like for the capacitor, and you get this expression for V sub L, and this one for V sub R. And we're going to be measuring the voltage across the resistor. And again, what we're going to do in this part is find the time in which delta V sub L over delta V is 1/2. So let's do that here. And follow these derivations because you're going to be deriving this in your lab. And so you're going to get the value for L, and you're going to get its uncertainty. So you're doing the same measurement. You're only doing it once, not 3 times. Okay? And you're measuring the voltage across the resistor, not the inductor. And you're going to do the complicated delta L calculation, but you only do it once. Show your work. Okay? Now, here's the problem. Our multimeter cannot measure inductance. The reason why is because if we wanted a multimeter that measured inductance, we'd have to pay a lot more for the multimeter. Okay? Adding that feature adds a lot to the cost of the multimeter. So, let's assume that this value is the following. Because they only quote it like this. So let's say it's 10 plus or minus 1 millihenries. Okay, let's say it's within 10%. And I can't see on it, I can't see my eyes are not that good. I can't see the code on it. If there's how well it's measured. Okay, I can't tell from, some inductors have a color code on them, like the resistor color code. And these have some writing on them, but it's hard, I have a hard time seeing what the uncertainty in the value is. So I'm just going to assume this. I'm just going to assume 10%. Okay. So this is the quoted value. You're going to make the measurement. Okay. Make sure you pay attention to the derivation I did today because they're going to be in your lab. And anytime you do a derivation, make sure you put comments or a description in your derivations. No comments, you lose points. You want to say what you're doing. Again, remember, imagine what your textbook would be like if there was no text in it, just equations. Would you be able to understand it? You're not writing to yourself, you're writing to someone else in your class. Okay? Questions on this? Concerns? Oh, what's this R? Oh, Chase, you have a question? You mean the extra battery? Are you talking about the extra battery in the signal generator? What extra battery are you referring to? Oh, you mean it's not a battery, just a little gray connector. Where did I put it? Oops, I just messed up. Hold on a second. I mean, this little thing, this came with the multimeter. Should be in the box. The yellow thing was the capacitor. Okay, this is just a random capacitor. It's a big one. Okay, that's not the yellow thing is not in your kit. This was just a big capacitor. So that one's not in your kit. So I don't know if you're referring to this or this. But the yellow thing is a big, giant, non-polarized capacitor. Oh, yours is blue? Your version of this is blue? Okay. So now let's go back and ask, what is our total in this circuit? Now, and it is the R equivalent of the circuit. But what is R equivalent of the circuit? What does it include? in this particular case. So this is really R equivalent. You're right. But what is R equivalent? Well, we got to think about what an inductor is. And we got to think about the signal generator. So our total R is the 47 ohms plus R, the signal generator. You're going to look up the value from the table you got last week. But there's one more. See, an inductor is a coil of wire. Right? An inductor is just a big coil. So it has resistance too. When we talk about inductors in class today, we're going to assume the inductors are ideal. But they're not. They do have a resistance. And the resistance value you can measure with the multimeter. So your equivalent resistance is the sum of these three. You got to take them all into account. Otherwise, you're going to get a big error in this calculation. Okay? So the last part, I'll just mention the last part. The last part of the lab, you're going to put a resistor, a capacitor, and an inductor. And if the conditions are just right, if you put in this signal, your output will can look like this. Okay. Actually, it's not really like that, but it's a bad picture. Your output can look like that with these three. It's called a RLC transient circuit. And maybe I should show you what the scope trace will look like. Let me change views so you get an idea what the scope trace will look like. This is data I've taken over the past year with the scope. Hold on, sorry. I just took snapshots. This is called an overdamped circuit. And you get a decaying sine function. So what you're going to do is you're going to choose a value for R from your kit, a value for L, which is going to be 10, most likely going to be the 10 millihenries. You only have 2 in your kit anyway. And then a value for C. And you want to observe this damping. Now, I'm going to help you determine your values of R, L, and C next week. So next week, what I'm going to do is, hold on, let me change views. I'm going to set up the differential equation. I'm going to apply Kirchhoff's laws. I'm going to set up this differential equation. It's called a second order differential equation. And I'm going to solve it for you using the method of guessing. Because I can't use the methods of Math 33. Although guessing is one of the methods. But I'll use some intuition to come up with the solution. And the conditions that you need to produce this underdamped circuit. And by the way, this picture has several examples. I did this with several different values of R, L, and C. Okay. So the one at the bottom, at the right there is nicely underdamped. The other ones are not. Okay. So this first one here and this second one here are nice examples. And so what you're going to try to do is build a circuit where you can observe this. And then you're going to measure the frequency of oscillation. Really, that's it. Okay, that's all you're really going to be doing for part 3. There's not a lot of analysis. At least you get an example of how you can get an underdamped circuit. Okay, but next week I'll solve the differential equation. Now Tyler made a video. I sent you the link to the video in the email last night. Please watch it. It's a very good video. He actually goes over how to use the signal generator at the end of the video. Okay, he goes through a lot of details. It's a 15-minute video which has all the details about all the equipment and everything. Questions? No questions? Okay. The capacitor, I'll show you what the capacitor looks like. I'm afraid to take it out of the circuit. That's the only problem. Okay, give me a second. Let me connect the camera. Usually the capacitor is easier to identify, but not always. Okay, I'm going to try to do this without taking it out of the circuit. Can you see the capacitor? That's what the capacitor looks like. It's kind of blurry. Can you guys see that okay?
Mm-hmm.
Okay. It's a it'll say 4.7 on it. Okay, and it'll have a plus and it'll have a minus sign to tell you that you got to hook up the negative to that side. Okay, so that's what the capacitor looks like. Okay, they all cut in different shapes and sizes. The one I showed you originally was a different one, but your capacitor will look like this. Okay. Yeah, and thanks for asking, because I assume that, sometimes I assume those are easier to see, but they're not. The inductor is actually hard to identify. Inductors are always harder to identify because sometimes they look like a resistor. Last semester, the inductor we had looked exactly like a resistor. It was very confusing to the students. And so Tyler got this other one, this black one, which is a little bit easier to identify. Okay, so this is the inductor. Okay, so you have two inductors. Like I said, you have two inductors in your kit. The smaller one is the 10 millihenry, which is kind of strange. This one's actually 1 millihenry. Okay, any other questions? For the analysis part 2 is the L calculated. Yeah, that's this. That's this equation. Okay. It's calculated from measured values, but yeah, this is the calculated value. Okay. And there is no measured value except whatever stated. So we're going to assume this is the quoted value. We can't measure the value with our tools. Oh, I'm sorry. Okay. So yeah, this is the calculated value. Sorry about that. Okay. And this is the measured value. I'm sorry, quote measured value. It's a stated value. Like we can't measure it. Okay. Are there questions? Yeah, we don't have a. Yeah, I brought some stuff from campus. I have a device that measures inductance. And they're all going to be, they're all varied. I mean, when I measured mine, it was like 9.8 millihenries or something. Okay. If we were on campus, we'd be able to measure it directly with a meter. Okay, if you guys don't have any more questions, I'm done. Please watch the video of this lab that I sent you. Okay? Please watch the video. And once you're done with this lab, you should get started on this. You can do this, like, you can do the capacitor lab one day, the capacitor part one day, it doesn't take long. The inductor part another day, and the RLC part another day. And neither one of them take a long time. It's up to you how you want to do it. But you should be able to do the capacitor part right now, because you've talked about capacitors already, and you know how to use a scope. The faster you get it done, the better. Okay? All right, so I'm going to end it here. We'll see you at 2 o'clock.